Okay, so let's continue. Last time we talked about service data units, protocol data units, splitting, multiplexing, many different things. We also talked about the OSI model consisting of, in principle, 7 layers with different names. And then we talked a little bit about the services which are provided by these layers. And if we start at the bottom, the physical layer, its service is to transmit bits over one physical link. So if we have an application program which is running on a host like this, and there is routers and so forth, until the application program which is running on another host, the actual bits which are transmitted over one cable here is the what's taken care of by the physical layer. The data link layer uses the physical layer, transmit of individual bits, to form units of bits, frames, which are transmitted back and forth here. The data link layer here, the entity of the data link here, talks only with the entity of the data link layer over one physical hop. Okay. The network layer uses the packet or the frame transfer service, which is provided by the data link layer, in order to transmit packets. And these packets are actually could be communicated over several entities here. And we will see later on this is needed in order to figure out a path through the network to go from this host to this host. That is the what is one of the tasks the network layer needs to do. So the network layer service can provide end-to-end communication service which is used by the transport layer. So the transport layer here, if one looks from a protocol point of view, there is an entity running in the transport layer at the host, and there is another entity at that host, and these are directly communicating with each other. Okay. The network layer, this is indirect, but it's also communications maybe. But here there is really end-to-end. So the layers which are on top of the network layer, so transport session and blah, 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 these are called end-to-end protocols because they talk from host to host. Okay. There is no, say, transport protocol layer in the router because it doesn't need it, right? It's not an end node. Okay, so there is no transport layer here. Okay. And then there's an arrow missing here. There should be one here also. So the application layer is also end-to-end. Yeah. So we should have done this the last time. But anyway, so if we talk about the lecture that we just had, what is true about encapsulation? And we have 3 statements here. That the higher layers include lower layer packets into the higher layer packet. Read that fast 5 times. No, okay. So the higher layer include the lower layer packet into the higher layer packet. Okay. It's a technical term that describes the data is placed between a header and trailer. That the lower layers include upper layer packets into the lower layer packet. So how many things? 1, 2, 3. 3 is the correct answer. So it doesn't necessarily have a trailer, right? So that's the caveat here. Okay, so it's almost true, but not quite. What's a typical layer n packet structure? Is it header, n layer PDU and trailer? Or is it header, n SDU and trailer? Or is it header and n layer PDU? Okay. How many things? 1, 2 and 3? Yeah. Okay, so this is also a little bit of a nasty question, but if we talk about layer N packet structures, we talk about its PDU, right? Okay, and its PDU consists of the service data unit that it got from above, and a header, and sometimes a trailer. Okay, so this is a possible correct answer. This one is wrong, because the header, the header is included in the PDU. The PDU is the whole thing, right? Okay, so it cannot be like this. And this one is also wrong here, because I mean, the PDU, you don't take a header and a trailer and then PDU in the middle. Service data unit, is encapsulated, and always a header, sometimes a trailer. But this was the only correct answer here. Okay. Again, I think what you should do is to look at this slide here and try to figure out what does this really mean. Okay. And I had an excellent question in the break here, which I might not have told you very explicitly. Okay, so here in the interface here between layer n+1 and layer n, so this NSAP, we said that here's some data going back and forth. So the service data unit from the perspective of layer n comes from above. So this is the payload that should be transmitted. What is not explicit in this picture here is that this entity here needs to tell this entity where this data should go to. So there is some address information and some other stuff going in parallel with this. But typically this is maybe just once if it's connection oriented, or otherwise it's provided for each packet that we transmit. So in this interface there is also control information, and that control information is then somehow affecting the header here. Right? It must somehow. Okay. But so the principle of encapsulation is basically to say that the data that the layer above would like to transmit is never touched and never inspected or used. But the control information is of course used, and that's used to affect the header. So for instance, if this is TCP and this is HTTP, HTTP here needs to tell the TCP unit, I would like to connect to the server at this IP address with this port. And that is affecting here, this one. But then the actual GET message and so forth is never touched or used by TCP here. Okay. Hopefully this will not be too much of a problem sorting this out. Okay, so now we're going over to lecture 3. And okay. So, more into an important thing called internetworking, and then a little bit on TCP/IP, how that works and how is that contrasted to the OSI model that we talked about earlier. And then, time permitting, we will go over to the physical layer a little bit, onto models there. So, terminology. We know that a network is a collection of nodes and links. We know that nodes are either hosts or routers. Hosts are those who are at the end of the network, end nodes that run software to support applications. So a laptop server, whatever. Router, some node whose purpose is to relay and route messages. Okay, so the interior working on the network. A link is a physical medium, this one, that connect nodes. So this is a network node. This is not a host. This is a host. This is a router, or actually a switch, but it's whatever. And here's the link. Okay. A layer is a set of communication functions that provide a service to the layer above by using the services of the layer below it. Okay. Service could be connection-oriented or connectionless. I won't go through all the details now because we just talked about it last hour. A protocol is a set of rules that determine how two communicating parties in the same layer interacts. Okay, so this is important. The same layer. Right? A layer can contain many different protocols, but not the opposite. A layer N entity, the entity here, is a piece of software or hardware that executes the protocol. Okay, and we can have several of those in parallel running at the same time in a host. Layer N entities at different nodes are called peer processes. So at 2 nodes, the TCP entities here are called peer processes because they are on the same level, the same hierarchy. Okay. Layers at the same node communicate by exchanging service data units. Okay. So here I got, so this is actually the point I made earlier. So if we look at the same node, data goes vertically in the stack, right? And it goes through this service access point, which is the interface between 2 layers. And the interface, one goes data, service data unit, and these control information, addresses and so forth. Okay, and that goes over this service access point. Service data units are encapsulated into PDUs. So PDU is a header, service data unit, and possibly a trailer. Okay. A layer can segment a service data unit into smaller pieces, transmit them individually, and then reassemble that at the receiving end. A layer may put several service data units into a single protocol data unit, and then disassemble that at the receiver. This is called blocking or aggregation. A layer can serve several entities in the layer above, so that's multiplexing, or use several entities in the layer below, that's called splitting. Sometimes we have specific names for PDUs, message, segment, packet, frame for these layers. But if we just say packets in general, it just means a block of bits that belong to each other, regardless of layer. OSI reference model, 7 layers in principle. In practice, we talk about the application layer consisting of the top 3 ones, still has number 7. Now, so let's go into the new things. Internetworking, what is that? Well, the internet is a collection of networks. So it's a network of networks. So in many cases, we have a network here, and this could be, for instance, the local Wi-Fi system here in this building. So that's a network. So that provides connectivity with every node which is connected to that one. So there are hosts connected to this one. But if my laptop, for instance, if I want to talk to the web server is then connected to some other network, maybe Ethernet network somewhere else. So this is a Wi-Fi network, this is an Ethernet network. This one could be fiber optical networks, this could be a satellite network. How do we connect these together, right? Then we use special network nodes which are called gateways. And a gateway is something that connects 2 networks. So a gateway needs to be able to speak the language of this network and the language of this network. So this one could, for instance, be a Wi-Fi router which speaks Wi-Fi with Wi-Fi clients, but then speaks Ethernet with Ethernet clients on the other side. Okay. So it's connected both to a Wi-Fi network and an Ethernet network. So it's a gateway between these 2 networks. And it provides connectivity over these 2 networks. And here's another gateway. And now we can add networks with gateways to expand this network, if we like, this network of networks. And the whole thing then becomes this internetwork. So an internetwork is a network of networks, and connectivity between the individual networks is provided by gateways. And now we can transmit information from a host connected to one network to another host, which is connected to potentially another network. Okay, so this is the power of internetworking, that we can add networks to this glue them together with gateways, and we can provide connectivity over this network of networks. Okay, so the biggest internet in use is of course the internet with a capital I. But there are smaller internets, like private networks, that are not connected to the big internet as we know it. Right? Okay. We talked about this OSI model, and we said that this is a theoretical model which has been very influential in how to think and talk about protocols. But the protocols which have developed for OSI is not used, essentially. The internet model is used heavily, right? This model is a little bit more, what should we call it? A little bit more loose in its, it doesn't really, it's not so clean, right? But it's also used. So we need to both know the clean model and the messy model. This one because it's easier to understand what the protocol really should be like. And the internet model is to understand how things are actually done in practice. Okay. Now, the internet model consists of 4 or potentially 5 layers, depending on which book you read. So it doesn't even have a consensus on how many layers there is in the internet model. In this course and in the book that we use, there will be 4 layers. The bottom layer here is called the network interface, and then there is the internet layer, transport layer, and application layer. There is no direct connection between the layers in the OSI model and the internet model. So the lowest layer in the internet model, the network interface layer, has basically layer 1 and 2 of the OSI model, and then parts of 3. While the internet layer here has parts of, it's basically the network layer in the OSI, but not some of that functionality here is actually found its way down here. So there is no direct connection between them. The transport layers are basically the same, and also the application layers. So even in the internet model, we call this layer 1, this layer 2, this layer 3, and this layer 4 perhaps. But the numbers are seldom used in the internet model. Basically we give them names instead. Okay. All right, so we have the numbers here of the OSI model, the names of them, and the names of the internet model here. The mapping between the numbers here and here, you should know, but you don't have to. When we talk about layer number 1, we typically talk about the physical layer. We never call this layer 1 to avoid confusion. Okay. I don't know if I was able to avoid confusion here, but anyways. So first of all, there is no exact translation between layers. The network interface layer deals with parts of the OSI network model also. The internet layer here in the internet model is the one that provides the connectivity between networks. So the IP layer, as we will see later on, from gateway to gateway. Okay, so internet protocol approach. We have IP packets, and that transfers information over an internet. So an internet is a network of networks. So we have a host and we have a host. These are the 2 end devices, and they want to communicate. And IP provides connectivity from host A to a router, to a router, to a router. And the IP layer in each router determines the next hop. So the network interface transfers IP packets over networks. So here we have a host, has a transport layer, internet layer, and network interface layer. We have a host here to the right also, where we have transport layer, internet layer, and network interface layer. And here we have a couple of routers, and we see that there is no transport layer here on top of those, because it's not needed. So if we want to transmit the information from this host to this host, this is what we do. I mean, there should be a nice animation here. Come on. Oh, you didn't see it. Okay, sorry for this. But anyways, so here's how the information goes. So suppose the information here should go here. It goes down first to the internet layer and then to the network interface layer. And the network interface layer provides connectivity over one network. So it could go like this over this network here to this network interface. So these two network interfaces are connected to each other. Then it goes up into the internet layer here to figure out, okay, what is the next gateway I should go to? And that's actually over this network, and then it ends up here. The next packet doesn't necessarily need to go the same way. It can go this way and to this one, right? So we don't know. But IP is responsible for maintaining paths through this internet. That is to jump between, jump over networks. That's IP's purpose. The network interface is to provide connectivity over that particular network. Okay. We will see an example. I'm sorry for the messed up slide here. Okay. So, TCP/IP protocol suite looks like this. So we have 4 layers: the lower layer, internet layer, transport layer, and application layer. So the network interface is at the bottom. So if we start at the bottom here, we have many different types of networks: Wi-Fi, Ethernet, LTE, ADSL, fiber optical networks, satellite networks, whatever. The IP layer provides connectivity over these networks. So then the transport layer can use IP to transmit between hosts. Okay? And these hosts can be connected to different networks or the same network, doesn't matter. IP takes care of everything here. And then on the transport layer, we essentially have 2 protocols, TCP and UDP, and which both of them use IP. And on top of that, we have the application layer. And here we have many protocols. HTTP, SMTP, which is the mail transport protocol, DNS that we talked about earlier, this is RTP, real-time protocol, you name it, FTP, many things here, right? But the key to success, why the internet model has been so successful, is the IP layer that does all the heavy work in hiding all the specific particular properties of the underlying networks, handle all of those, and present a unified interface to TCP and UDP, which is basically to transmit packets over an internet, a network of networks. So the key to success here is the IP layer, I would say. And it hides the mess, this mess, for TCP and UDP. So what service does the IP layer provide? Well, the IP layer provides a service up to TCP and UDP or whatever protocol which is in the transport layer here. And it provides a best effort, connectionless packet transfer service. So it can transmit packets, so blocks of bits. It does that in a connectionless fashion. And it's also best effort. And this is a thing we haven't talked about. But best effort basically means it doesn't guarantee anything. It doesn't guarantee that the packet actually reaches its destination. It does its best, but you know, things happen and packets are lost. Okay. TCP, what it does, it uses this service to provide to the protocols above it a reliable connection-oriented stream service. Okay, so it's reliable in the sense that it says, okay, if you give me HTTP, if you give me a service data unit, I guarantee that it will reach the destination. Okay, and I also, this is not so necessary for HTTP to know, but it uses a connection, it provides a connection-oriented service to HTTP. Well, it's important for it maybe. And it's also a stream service, meaning that it can take individual bytes. It doesn't necessarily have to have a limit on the number of bytes. Just give me a stream of bytes and I will transmit for you, and I will do that in a reliable fashion. So the stream of bytes you give me, I will present them at the receiving end in order, error-free, always. Okay. Now, if something major happens, you know, a router explodes or something like that, okay, then I can give up, right? But then I will tell you that I failed. Okay? IP will not tell TCP that it failed to transmit the packet because it's a best effort service. So TCP refines the service of IP into something which is more valuable, right? And this service is then appreciated by a number of protocols up here. Now, why do we have UDP here? Well, UDP provides a best effort connectionless datagram service, and datagram and packet is essentially the same. So UDP is a very thin wrapper around IP essentially. It doesn't do much, really. So, but there are protocols on top of this, RTP for instance, that is, and DNS, which is happy to work over UDP. Okay. Because for them it's not so critical that the service is reliable. So it's happy to use the UDP service. And the good thing about UDP is that it's quick and doesn't require a lot of resources. So it's a quick and dirty solution. So maybe this is your Volkswagen and this is your Porsche, right? Okay. Sometimes it's nice to have a Porsche, but you don't want to pay for a Porsche. So you use a Volkswagen instead. Okay. All right. Who decides about these protocols? We talked a little bit about this. I mean, who does this, right? And protocols are super important because they specify how things are supposed to work. So we need to agree upon them. And basically it's like we need a United Nations for computer networks. So there are different types of these standardization bodies that decide about these protocols. So for instance, there is these ITU, IEEE, IETF, W3C, and 3GPP. And they decide over different types of protocols. So for 3GPP, it decides over GSM, 3G, LTE, 5G, 4G, and so forth. So they are in charge of this. This thing decides about web standards, so HTML, the syntax for that, and so forth. The Internet Engineering Task Force is what this means for. They're responsible for TCP, IP, and all these protocols. So HTTP, DNS, and so forth. IEEE takes care of typically lower layer protocols like Ethernet, Wi-Fi. That's IEEE standards. ITU here takes care of some more, different things. Everything from MPEG-4 is a video encoding format to how ADSL works. Okay. And all of these needs, of course, to agree to make a system work. And sometimes it's messy, and the standards which comes out of these are not maybe the technically most suitable ones. Because, for instance, when it comes to LTE, for instance, this is a compromise between all the players in that business. So Nokia, Ericsson, and Huawei need to agree upon things. Is that difficult? Yes. And why is that difficult? It's because Ericsson owns patents for this technology, Huawei for this technology, and Nokia for this technology. So what do you think they will promote in the standard discussions? Their own IP portfolio, of course, their own technology, which they own patents for. So this is a commercial fight, I would say, to provide a standard. So it's not always optimal from a technical point of view, but hopefully it works, right? Because both Nokia, Ericsson, and Huawei needs a system to work, otherwise they cannot sell their stuff, right? So they have an interest to agree, but they also have an interest to agree upon things which they can make money on. Yeah. Okay. Back to technology, it's easier, right? So, internet names and addresses. Internet names, we already seen these. What are these? These are unique and easy to remember things that identify hosts. So they're independent of physical location, and they have two parts, a host name and a domain name. So this www.chalmers.se has two parts of it, the host and the domain. So there might be many hosts in this domain, and there is one which is called www, conveniently hosting the web server. But there could be one which is the mail server host, or it could be something else, right? Typically, there are several hosts running the web server also for efficiency and load services. But at least there are two things here, the host and the domain. Internet addresses are IP addresses, and they uniquely identify a network interface card. Okay, so a network interface card can have actually several IP addresses, but an IP address is not pointing to two different network interfaces. In this thing, there is a Wi-Fi network card, and it can have several IP addresses, but the IP address to this Wi-Fi card cannot be used by the Ethernet card, which is in this one too. So if I plug this into the wall using this and the proper Apple adapter like this, then this one gets an IP address, and then the Wi-Fi gets another IP address. Sometimes you can configure Wi-Fi to have several IP addresses, right? But it will never be the same IP address which is for this one. Okay. So IP address points to a network interface, but a network interface can have several IP addresses. A node can for sure have several IP addresses because it can have like the wired IP, the Wi-Fi IP, and so forth, right? So we can reach a host through typically through several IP addresses. Typically, we can if it has, of course, but it could all have a single one. Routing, that is to find the path through the network, is based on the destination IP address, obviously. And the IP address has two main parts, a net ID and a host ID. And so if we remember, a typical IP address is 32 bits for IP version 4. There is also an IP version 6, which I believe has 128 bits, if I remember correctly. But anyways, let's go for IP version 4. We have 32 bits here, and they're in this format typically. So here we have 8 bits, 8 bits, 8 bits, 8 bits. 8 times 4 is 32 bits. So with 8 bits, we can have a number between 0 and 255, right? So here's 129, 16, 17, 21. And somewhere there is a boundary here which identifies the network, and the later one identifies the host. And this is useful for routing, because if we are doing routing, we route towards the network first, and once we reach the network, we route towards the host on that network. So like when we sent a telegram from Alice to Bob, it's first routed to Borlänge because that's where Bob lives, and then once in Borlänge, it's routed to Bob. So it's out of efficiency purposes. We have this hierarchy. Okay. Physical addresses. These are addresses which are on the local area network. In the particular network, we have physical addresses, and they basically points to. So when this is attached to an Ethernet network, this one gets a physical address. Okay. This box might have an IP address, but it also has a physical address. This one has a physical address. Okay. And the network uses this physical address to address transfer packets on that network, on the same network. IP addresses needs to be translated, or the technical word for that is to resolve, to physical address before transmission over the network. We see an example shortly. Okay, so one physical type of address is this Ethernet, which uses 48-bit addresses. So each Ethernet network interface card, you know, the ones in here or the ones in here, has a globally unique medium access control address, MAC address or physical address. So a MAC address, might be familiar to you, is a physical address which identifies uniquely that chip which is in here. Okay. while IP addresses changes depending on where you plug it in, right? But the physical address is the physical address to this chip here, right? This is, of course, in theory. In practice, it's a little bit different because you can reconfigure these MAC addresses for some of these chips. But in theory, you should not do that. So when you manufacture this chip, every chip gets a unique physical address. So the first 24 bits in this address identifies the manufacturer, and the second 24 bits is the serial number. So, for instance, one of my Ethernet cards in this one is called this. Okay, so here the specification is, we see here we have numbers, colon, number, colon, colon, like this. And between the colons there is a hexadecimal number. So it's a number. No, there are two hexadecimal numbers. Okay, so 2 and 4 are the two hex numbers. So, and hex has 4 bits into it. So this is 8 bits. No. Okay, so let's start again. A hexadecimal number is 4 bits, right? It's 0 to 15. Okay, 2 of those is 1 byte, 8 bits. Okay, 1 byte, 1 byte, 1 byte, 1 byte. You count them, it's 6 bytes, 48 bits. Okay, now I got it right. Sorry for messing this up. But anyways, the first one here identifies this as an Apple chip. Okay? So if you look at your MAC addresses, you can figure out where they come from. Broadcom, Apple, whatever, right? Some of these companies you may never heard of. Apple is well known, I guess. Okay, but that is in theory, of course, because you can also reconfigure these MAC addresses. But the idea is that there should be no, the theory is that there is no duplication of this. So there is no 2 Ethernet cards with the same MAC address in the world. Okay. So how is this used? Well, okay, so let's have a network here consisting of a server, a workstation, and PC. So these are 3 hosts. Okay. The server and the workstation are interconnected over an Ethernet network. The PC here is connected over a very simple network, which is a PPP network. A PPP network is the simplest you can think of. It consists of 2 things, one end, and a cable between them. Okay, so it's a super simple network, but it is a network, right? It uses a specific protocols here, which is different from the Ethernet protocol. Okay, so the Ethernet here has a net ID, and let's call it 1 for simplicity. It should be the first part of the IP address, but for simplicity, let's just call it 1. The PPP network has network ID 2. So the IP address on the PPP protocol here is 22 for the PC and 21 for the router. And 2 because it's network 2, and 1 because it's the node 1 on that network, which is the router. And node 2 on node 2 on network 2 is the PC, so it has 22. The router has an interface which points towards the PPP network. It also has an interface towards the Ethernet network. So it has an IP address on this side also, which is 13, meaning it's on network 1 and it's node 3 on that network. So the router at the same time has 2 IP addresses, one here and one here, because it's connected to 2 networks. Okay. The workstation here is only is connected to network 1 and is node number 2. The server is 1 connected to network 1 and it's node number 1. Okay. So the green ones here, we can think of them as the IP addresses. Questions on that before we continue? Okay. So we see here that a device can have several network interfaces and therefore several IP addresses. Okay, So the server is 1.1, the workstation is 1.2, and so forth. Then there are also physical MAC addresses here. So the network interface card in the server has also a MAC address. So it has an IP address, the server has an IP address, but the network interface card in the server, one of them, has a physical address also. Let's call it S. Okay, so the server has an IP address and a physical address. The workstation has an IP address and a physical address. The network interface card here has a physical address. And the router also has it. Now, there is no physical addresses here, and the reason for this is that basically, if the network consisting of two nodes, if you know you're the transmitter, the other one knows it's the receiver. There is no need for addressing here. Right? So if you receive something, you know it's for you. If you transmit, you know it's only going to go to the other end. So there is no need for addressing here. Okay. Let's see now how we transfer information over this network of networks. And we remember the principle of encapsulation. So on the IP layer, we have an IP packet that consists of an IP header and the IP payload. And the IP payload might be something that we got from TCP or UDP. We don't know. It's something. But we have an IP header here. And this IP packet is then encapsulated into an Ethernet frame, which then adds an Ethernet header and an Ethernet trailer to the IP packet. So we see that the IP packet just copied down here. So the Ethernet header here consists of source and destination physical addresses, and it also has a piece in it that identifies this as an IP packet. So at the receiving end, we know to which protocol to send this to. This trailer here is a frame checksum, which is used for error control purposes, to check basically that these bits are correct. We'll talk more about that later on. Okay, so back to our network, which consists of 3 nodes and a router. So 3 hosts and a router, and now we would like to transmit some information here. So suppose the workstation would like to transmit some information to the server. Okay. So at the workstation, we have a protocol stack consisting of an IP layer and Ethernet layer. Of course, there is some layer above the IP layer and so forth, but let's just concentrate on the lower parts here now. So in the IP header of the IP packet, among other things, it contains the source and the destination IP addresses. Okay. So this is an IP packet that comes from 1.2, the workstation, and it should go to 1.1, the server. So the IP packet source address is 1.2 and the destination is 1.1. Okay, so what happens next? Next is that the IP layer here maintains a table that maps IP addresses to physical addresses. So it looks in this table at the workstation and figures out that 1.1 is actually on the same network. Okay, because it looks here, network number 1. Well, I know I'm on network number 1. Okay, so it's on my network, and it's on it's node number 1 on that network. So it has to have some physical address. And as a matter of fact, I know the physical address. It's S. Okay, so the IP layer here knows that 1.1 is a node which has physical address S. Okay, so this is used by pushing down the IP packet down to the Ethernet layer and telling it, okay, so this IP packet should go to a node who has physical address S. So it should go to S, right? It should go here, and it comes from W because that's the physical address of the workstation. Okay, so now we have an Ethernet packet here, and the network interface card in the workstation is then transmitting this over to the server. Well, actually, what it does, it puts it out on the LAN here, and every node which is connected to the LAN picks up this packet, but it's thrown away if it's not to you. So only the server accepts this packet because it looks at the destination address and realizes, okay, it's to me. So the server network interface card inspects picks up this Ethernet packet, and then looks at the header here and realizes, okay, it's an IP packet, and then it delivers it up to its IP layer that then do the further processing. Okay, so IP layer at the source encapsulates into a frame at the source, sent over the physical network, picked up by the correct receiver, and then pushes up the IP packet at the destination. Questions? Okay. So now a little bit more complicated scenario where we want to send an IP packet from the server to the PC. And here that entails transmission over two networks in this case. So this is where internetworking comes into play, right? The previous example, we could do that without really IP because we could do that over Ethernet right away. But it starts the same. It goes now from 1.1 and it should go to 2.2. Okay, 1.1 is this IP address of the server, and 2.2 is the IP address of the PC. The IP table here realizes, okay, this should go to 2.2. It should go to some other network. I don't know what to do with this, but I know it should go to some other network. So I will send it to my default gateway or my default router. So it then first wants to transmit it to the router and then say, okay, the router can handle it from there, right? But the first thing I need to do is to transfer this IP packet on its first hop, and that is to the router. Okay, so the IP table say, okay, this should be sent to the router, and then we encapsulate that into an Ethernet frame, and the Ethernet frame should have a source S because it goes from the server, and it should have a destination R because that's the router. Okay, so we form an Ethernet frame like this, IP packet, and then from server to router. The Ethernet frame is transmitted over the Ethernet here and is picked up by the router. So the router now has the frame like this and starts to process that. It looks at the protocol field inside the header here and realizes this is an IP packet. So it should go to the IP layer, not to any other protocol layer which is above it. So it delivers it to the IP layer. Now the IP layer takes over. So it inspects then the destination address 2.2. Okay, so the IP layer at the router here at this end realizes, okay, so it should go to network number 2. But it happens to be, okay, I'm actually connected to network number 2, so I need to transmit this over this link. If it should go to network number 3, maybe it goes out to another link, or network 4 to some other link. But this one should go to network number 2. Okay, so it pushes it over to the IP layer on the other side. Okay, and then the IP layer here realizes, okay, it should go to 2.2, which is actually my network. So what do I need to do then? I need to figure out the physical address of 2.2, which is very simple since it's PPP here. There is no physical address, so there is no translation between IP address or not. I just realized that this should go to my network, so I can just transmit that. So then we encapsulate the IP packet into a PPP frame, so it has a very thin protocol header here. But anyway, so this is then transmitted over the link, and then it's received by the PPP layer in the PC, and it realizes it's an IP packet and it's delivered up here. Okay, so all of this work has now enabled this IP packet to be transmitted first over an Ethernet and then over a PPP link and be presented to the IP layer at the destination. Okay. Questions? This is a lot of information, right? But go home and stare at this a little bit to try to decipher what's going on. Okay. Okay. IP provides connectivity over multiple networks. Ethernet provides connectivity over Ethernet, one Ethernet network. PPP provides connectivity over a PPP network. Right? So IP is above these two network layers to provide connectivity from host to host, regardless if it's on the local network or some other network. So it provides this network of networks. Okay? Oh, what time is it? I mean, if I drag away, you know, more than a minute or so before the break, you need to tell me. Otherwise, I'm too excited about this, right? So let's take 15 minutes now. So reconvene 10 after.